This lesson is on covariance and correlation. We're going to begin with covariance, and the definition for covariance between two random variables x and y is the covariance of x and y is equal to the expected value of x minus e of x times y minus e of y. And if we multiply that out and use properties of expected value, similar to how we did in variance, we'll have the covariance of x and y is the expected value of x times y minus the expected value of x times the expected value of y. So the covariance relates the change in one variable to another. It tells you if x changes, even if x goes up, is it likely that y will go up or down, or are they even related at all? So let's take an example. We're going to look at the standard coin flip example. A coin is flipped 3 times, and let x be the number of heads in the first 2 flips, and y is the number of tails in the last 2 flips. We're going to find the covariance of x and y. So if you take a minute to pause and think about it, they do affect each other in some ways. So the middle flip, if it's a heads, then x is higher, and y will be necessarily lower, right? Because it can't. Y is going to be 0, 1, or 2, and it can't be 2. And y, if that middle flip is a tails, will be higher, and x is going to have to be lower. So they have some kind of negative covariance. So let's look at the sample space and all possible points. So here's the sample space of outcomes of flips with 3 flips. There's heads, heads, tails, heads, 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 tails, tails, and so on. So in each row, I've written what value x and y will be. In this first row, 3 heads are flipped, which means that x would be 2 and y would be 0. And so x times y is 0. Let's take an example like heads, tails, tails. So x is the number of heads in the first 2 flips, and there's 1 heads in the first 2 flips, so x is 1. Y is the number of tails in the last 2 flips. So the last 2 flips have 2 tails, and so y is 2, and 1 times 2 is 2, so x times y is 2. There are 8 outcomes, so to find the average values of x, y, and x times y, you can add all the numbers in a column. So if we wanted to find e of x, we would add all the numbers in this column and divide by 8, because there are 8 equally likely outcomes. So doing that, we get the expected value of x is 2 plus 2 plus 1 plus 1 plus 1 plus 1 plus 0 over 8, which is 1. And then y, you could do 0 plus 1 plus 1 plus 2 plus 0, so read down the column, and you get 1. And then taking the products of each one, we can find the expected value of x times y is 3/4. So the covariance between x and y is e of xy minus e of x times e of y, or 3/4 minus 1 times 1, which equals negative 1/4. So there's a negative covariance because if one variable goes up, the other one's expected to go down. And notice that this is slightly different than variance because these can be negative values. So let's look at a few properties of covariance. If x and y have positive covariance, this means, as I've said, that if one of x or y increases, it's likely that the other also increases. But negative covariance would mean if one increases, it's likely that the other one decreases. Some of the mathematical properties of covariance are that the covariance of x with itself is just the variance of x. It doesn't matter which order you compute them in. So the covariance of x and y means the same thing as the covariance of y and x. If a is a number, and we do the covariance of a times x and y, you can actually pull the a out of the covariance, so it's a times the covariance of x and y. And the covariance can be broken up over sums. So if we want the covariance of x and y plus z, that's the covariance of x and y plus the covariance of x and z. And finally, if x and y are independent, then their covariance is 0, because if one goes up or down, that doesn't tell you any information about the other one, since they're independent random variables, so it doesn't tell you if the other one's going to go up or down. However, a covariance of 0 does not mean that they are independent, so it's a little bit of a trick there. If they tell you this x and y have covariance 0, a lot of people, whenever they're first learning probability, will accidentally assume that x and y are independent, but that's not necessarily the case. However, independent random variables always have covariance 0. So let's go through the proofs of these facts. Number 1 is that the covariance of x with itself is the variance. And this just follows from the formula. So it would be the e of x times y, which is x and x, so we get the expected value of x squared minus e of x times e of y, but that's e of x times e of x, which is e of x squared. So we get this e of x squared minus e of x quantity squared, which is the variance of x. And also number 2, which is that the order doesn't matter, is just because multiplication is commutative, essentially. So covariance of x and y and covariance of y and x are both just e of xy minus e of x, e of y. And you could do e of yx minus e of y, e of x, but it's the same thing because it's just multiplication. Next, we can use the formula to show that we can plot a constant. So number 3, if a is a number, then we can pull it out. Number 3 here, the covariance of ax and y is e of axy minus e of ax, e of y. But in both cases, the a can be pulled out. So this a of exy is a times e of xy, and the e of ax is a e of x. And then factor this a out from both terms. So these two terms, we're going to just pull the a out and put everything in parentheses. And the bit in parentheses here is the covariance. So it's just a times the covariance of x and y. It just works out algebraically, as does number 4. So the covariance of x and y plus z, if we start with that, covariance of x and y plus z, this means e of x times y plus z minus e of x times e of y plus z. But in the first part, we can distribute the x, so e of xy plus e of xz. And then also, we can use the linearity of expectation to write e of y plus z as e of y plus e of z. So that's this line. And then, using linearity of expectation, we get e of xy plus e of xz. And then here, we're just distributing negative e of x. So we get negative e of x, e of y, minus e of x, e of z here. And then it's just a matter of reordering things. So this e of xy stays in front, but then we're going to put minus e of x, e of y next, then the plus e of xz, then the minus e of x, e of z, which is covariance of xy here. So these two give us the covariance of xy, and these two on the end give us covariance of xz. So that's just another way to write covariance of xy plus covariance of xz. And the last claim is the independence. So if x and y are independent, then e of xy is e of x times e of y, and therefore the covariance is e of xy minus e of x, e of y is just 0. However, we could construct random variables x and y which have covariance 0 but are not independent. So let's let omega be the sample space 1, 2, 3, 4, and each point has probability 1/4. And x and y are defined as x of 1 is negative 1, x of 2 is 1, x of 3 is 0, and x of 4 is 0. And y of 1 is 0, y of 2 is 0, y of 3 is negative 1, and y of 4 is 1. So notice that x times y is always something times 0. So if it's 1, we're going to get negative 1 times 0 is 0. If it's 2, we'll get 1 times 0 is 0. If it's 3, we'll get 0 times negative 1 is 0. And if it's 4, we'll get 0 times negative 1 is 0. And also that the expected value of x and the expected value of y are 0, because we get negative 1 times a fourth plus 1 times a fourth plus 0 for x, and 0 plus 0 plus negative 1 times a fourth plus 1 times a fourth just cancels, so we get 0. And therefore, e of xy minus e of x, e of y is just 0 minus 0 is 0, everything 0. So the covariance of x and y is 0, but x and y are not independent, because if we condition, for example, on x equals 1, then we know that y is 0. It depends on x, so it can't be 1 or negative 1 or 0. Also, it just fails the definition. It looks like it's how I showed this. So the probability x equals 1 is a fourth, and the probability y equals 1 is a fourth, but the probability x equals 1 and y equals 1 is 0, so it's not the product, which if they were independent, it would be 1/4 times a fourth, or 1/16. Now we're going to go on to correlation. And the correlation of x and y is just the covariance of x and y divided by the standard deviation of x times the standard deviation of y. So what this does is it takes the covariance and then scales it to be between -1 and 1. And that's this first property here. So the correlation of any two random variables is between -1 and 1. And we're not going to prove this here. It uses a slightly more advanced analysis fact that I'll probably prove in a later lesson, but I felt like it was a little out of place here because most of this is just simple algebraic manipulation. For any random variable x, the correlation of x with itself is 1. So here we just have correlation of x and x is the covariance of x with itself over its standard deviation squared. But both of those mean the variance of x, right? The covariance of x with itself is the variance of x, and the standard deviation squared of x is its variance. So we have variance over variance, which is 1. If y is a positive multiple of x, the correlation is 1 also. So in other words, if like y is 2x or 3x, so if y is ax for some x bigger than 0. In this case, we've shown before that the standard deviation of y is just a times the standard deviation of x. So using the definition of correlation, we have x and a of x. The a can come out, so we have a times the covariance of x with itself divided by a times the standard deviation squared, and again, both of these are the variance, so it's a times variance x over a times variance x, which is 1. And it's the same sort of algebra whenever y is a negative multiple of x. But the correlation of x and y will be -1 if y is just a times x for some a less than 0. In this case, the standard deviation of y is -a times the standard deviation of x, because standard deviation is always positive. So if a is negative, a is less than 0. A is a positive number. And then we just plug this stuff in again. So correlation of x and a of x is a times the covariance of x and x over -a, the standard deviation of x squared, which is -a variance x over a variance of x, or -1. And finally, the last property is that if x and y are independent, their correlation is 0. And it follows immediately because the covariance is 0. So the correlation of x and y is the covariance of x and y over sigma x, sigma y, but covariance of x and y is 0. So this is just 0.